Ian, despite the fact that you see him all the time here, is actually at Warwick. Anyway, he'll tell us today about the amazing things you can do in small space.
Yeah, all right. Thank you so much, Avi, for the introduction and for inviting me. It's always good to be back at the IAS. Yeah, I'm going to be talking today about this problem called the tree evaluation problem. I'm going to talk about what it is, why we care about it, and what's been happening with it lately. So to talk about the goal right up front, the whole point of what we want to accomplish is to separate time and space. So you've probably seen these complexity classes before. We have this class L, which is every problem that we can solve efficiently in space. And we've got P, which is the problems that we can solve efficiently in time. And we know that anything you can solve efficiently space-wise, you can solve efficiently time-wise. But for a long time, we've been trying to figure out if the other direction holds. If everything you can solve efficiently time-wise, you can solve efficiently space-wise. And
so you suppress log space for a reason? I mean,
well, so there's my log space.
Okay,
sorry.
Yeah.
So here's today's the more rich diagram of complexity classes for today. So we're dealing entirely inside polynomial time. These are very efficient space or time efficient problems. So P is everything that can be solved in polynomial time. That's what we consider efficient. And at the bottom end, we have everything that you can solve with small formulas. These are Boolean formulas with ands, ors, and not gates, each of which takes 2 inputs, and the depth is at most logarithmic. And this logarithmic is what we consider efficiency with regards to formula depth. And likewise, for space, we consider logarithmic space to be efficient. So that's this class L that I talked about before. And in between, we have some other classes that you've probably dealt with before. We've got non-deterministic log space. We have NC2, which is the same as this NC1 here, but with a log squared. And then at the top end, we have polynomial time. But for today, log space is really going to be the protagonist. And so our antagonist will be this function called tree evaluation. In its full generality, the tree evaluation problem is parameterized by 3 numbers, K, D, and H. K is an alphabet size, D is a fan-in, and H is a height. So true to the name, we are given a rooted tree where the fan-in is this parameter D, the height is this parameter H, and what we mean by alphabet size is that each of the leaves is going to be labeled with a number between 1 and K at the bottom. That's going to be our alphabet. And that's going to be our alphabet without loss of generality, because at every internal node, the input has to specify an entire function from the inputs to the output. The inputs are D numbers, 1 to K, and the output is 1 number, 1 to K. And so the evaluation is the natural bottom up. You have one of these nodes sitting right above these leaves, and so this node takes in all of its corresponding leaves, the values at all of its corresponding leaves, evaluates the function, spits out a number. That holds true for everything here. And then in the next layer, you take those numbers, spit out a new number, and so on and so forth, up until you get to this root node, and whatever value it spits out, that's going to be the output of your function. And all of this is the input to the problem. All of these functions have to be specified in their entirety. So just as a sanity check, the size of this problem is something like K to the D is the number of nodes in here. D to the H is the number of nodes in here. And each of these things takes K to the D. You have to specify K to the D spots with, say, log K bits per. So that's roughly what we're talking about. And we're going to mostly focus on the simpler version where the fan-in is just 2. So you take in 2 numbers and you spit out 1 number. Take in 2 numbers, spit out 1 number, and go all the way up. But I mentioned the fan-in one because there's the alternate version, which is a little bit older than tree evaluation, where instead of fixing the fan-in, you just fix the alphabet to B0 ones. So you take in some number of bits, D bits, and spit out 1 bit, and do this the whole way up. This is sometimes called iterated multiplexer. So that's the problem. And I told you we're trying to separate time and space. So first of all, this thing had better be efficient with respect to time. And the description that I gave you of the function is just a polytime algorithm. start at the bottom, look at every number, use it to evaluate the nodes right above the leaves, use those to evaluate the next nodes up, and so on and so forth. So this thing is in P, and even in this lower class NC2. So it's not even the hardest problem in P, most likely. As for hardness, if you just fix the fan-in and the alphabet size to both be 2, so bits and 2 children at each node, this thing is basically an NC1 circuit. NC1 is and, ors, and nots of log depth. This thing is arbitrary functions of log depth. They're roughly the same. Certainly you can capture NC1 using this tree evaluation. So tree evaluation sits in this range. Again, it's probably not the hardest thing in P, and by a dumb argument, it can capture NC1. But the trick is that we actually think that this is a very hard function. So this is an old conjecture stated in a different language by Karshmer, Raz, and Vickerson. And it says that this iterated multiplexer version, where you have just Boolean alphabet, this thing is not in NC1. So there are no efficient formulas to compute this function. And then the story for our talk begins in 2012, or rather in a talk in 2009, where Cook, Mackenzie, Ware, Braverman, and Sampana conjectured that this problem is also not solvable with respect to space, where now they chose to vary the alphabet size instead of the fan-in. So they conjectured that this would be the problem that would show that time and space are not the same thing. And what's the logic? Because again, this thing is probably not even the hardest problem in P. Why wouldn't you just pick circuit value problem or some P complete problem? And it's that we have a nice logic that characterizes the hardness of tree evaluation, and it's called composition. Now I'm going to talk just at a high level about why the space complexity of tree evaluation might be hard, and it's as follows. If you want to compute tree evaluation, your ultimate goal is to compute the top node. So you want to compute this root. And to do that, you're going to have to figure out what the value is on the left and what the value is on the right. So let's say I'll give it to you. I'll give you the left-hand node. You can just have the value for free. I won't charge you space-wise for it. And so now all you have to do is compute the right-hand node. Well, you've now remembered some log k bits, and you've moved to a height h-1 instance, because tree evaluation, it's just, you just shave off a layer and it's the same function. So now let's apply the same logic. If you want to compute this thing, the right-hand node, which is all you need to finish the function, you need to do the left and the right. So let me give you the left for free. You're going to remember it in log k bits, and now you have to compute the right. And the problem is, if you work all your way down, you end up storing h different values, each of which takes like log k bits to remember. And if you work through the parameterization of tree evaluation, this is not good enough. So in fact, this conjecture by Cook et al. Was that tree evaluation requires this much space asymptotically. H values of log k bits need to be remembered, which would give you a log squared space algorithm, which is well outside of L. This would be enough to separate, this would be enough to separate L from P.
So then that's your high choice for K's and.
Yeah, so you can pick the parameters however you want. You can't pick, because of this size, you can't pick k to be bigger than like poly n to the epsilon or something, and you can't pick h to be bigger than log n. Because you have to specify the entire functions at all these nodes, the problem size just blows up too quickly. But they conjecture that pretty much no matter how you set h and k, these are the asymptotics. And so they had some partial results where you just fixed the h to be 3 or something, and it was roughly log k bits. 3 log k bits. But of course, since we're talking about asymptotics, we care about h getting bigger and bigger with respect to n. So yeah, think of h as like log n and k as like n.
And what should I think of D as?
D would also have to be something like log n, but we won't deal with D until the very end of the talk, so you can just really focus on the fan-in 2 case for a while.
The conjecture applies to D equals 2.
Yeah. So this is actually the conjecture where you fix D equals 2. The conjecture for the unbounded fan-in case is that it requires something, in the case where k is equal to 2, of course, this factor disappears. That conjecture is like DH is the formula depth. So that was the KRW conjecture, or a consequence of it. I might have a slide on that. So let me just say that this conjecture was very quickly proven for a number of natural restrictions on, so they model space, of course, by this non-uniform model called branching programs, which we may touch on later if there's time. But this is a version of space where you can put natural restrictions on it and then prove the lower bounds you want to prove, converging on real space lower bounds. And they proved it. So they proved it for this thrifty restriction, which is a very tree evaluation specific restriction. But they proved it for the more general and very well studied read once model. So if you can only read your input once, which the natural polytime algorithm for tree evaluation does, you just look at each number once and you work your way up. If you fulfill that restriction, you can't get better than log squared space. And in fact, later on, it was shown that both of these results hold even in the non-deterministic case. So now people were thinking that maybe this could even separate NL from P. And there was really no work to contradict this directly. There were no, I don't know what a restricted upper bound would have looked like, but suffice it to say there was a lot of faith put in this conjecture. Steve Cook even put $100 on as a prize on this. If you could show anything better than log squared, you could get paid that much, which.
Anything better than log?
Log squared n for the space. Anything better than this?
If you ask for an upper bound.
For an upper bound, if you can get any upper bound. Oh yeah, you don't get paid if you get a lower bound of log squared n. You just win stock best paper. Yeah, okay, so this was the old KRW version of it, and so very similar logic. Now it's not remembering values, it's about function or formula depth, but just suffice it to say this idea of composing functions in layers and trying to get hardness from that has been around for a long time and was studied very much in this form. So things were going good, and now we're going to talk about the other side of it. We're going to talk about those sweet, sweet $100 upper bounds. So first, I want to ask any questions. Cool. So the story of the upper bounds for tree evaluation really starts with this result by David Barrington back in the mid-80s. So he showed that this class of problems that can be solved efficiently by formulas, aka in logarithmic depth formulas, NC1, can be computed by this really nice space model called permutation branching programs. And the cool thing is that the length is efficient, polynomial, and the width, which you can think of as the memory that you're really holding about the function, is 5. So you're saving a constant amount of memory and computing this whole thing. Now,
just wondering statistically, has anybody never seen Barrington's theorem?
Oh, it's very cool. So we're going to see a proof of a generalization today. So you'll get the broad strokes of it, but if you can dig up the paper, you should read it. It's very nice. We're going to go into a generalization because it's going to give us more of a flavor of what we actually want to deal with, which is tree evaluation. So this is by Benner and Cleve just a few years later. And they showed at a high level, what they showed is that sharp NC1 is an L. And sharp NC1 is like this Boolean NC1 that I told you about before, a logarithmic depth formula. But now, instead of having these and or gates, you actually compute plus and times. So you start with bits, and that's all well and good. And now instead of doing Boolean logic on it, you just treat them as natural numbers. And so at the end of this, you're going to spit out some big number. And it's called sharp NC1 because it corresponds to counting acceptances in NC1 in some way. But the important thing for us is that it generalizes NC1, and it's not at all obvious before Benner and Cleve that it's in log space. And the reason why is because the same compositional logic I said before applies. If you need to compute this top level, say plus or times gate, you're going to have to compute the left and the right. And if you compute, say, the left and remember it, and then you move on, these numbers, just based on the height, can get up to something like log n bits. So why is it not the case that you have to remember log n numbers of log n bits, giving you the same log squared n space up lower bound that we conjectured earlier for tree evaluation? Their result really does say that tree evaluation is easy as long as your functions are very, very well structured on the interior. In other words, they're only plus and times, say mod k or whatever. So this was very surprising in light of this idea of composition. And we're going to go through the proof today. And I want to just start by saying they find, in a weird way, a way to use the same space for two different things at the same time. So space can serve many different purposes. It can be, namely, something that you can use to store values that you care about. So over here, that would be like putting these values aside for later. And you can also use it to do your computations. You know, you have two values and you want to take their plus and their times. So you just do the operations in space. And they found a way to do both of these things at once. So the model that they introduced is, well, it's an older model, but the model that they pulled back from the 70s is called a register program. In a register program, you can think of your memory as just being chunked up into blocks where each block remembers some number that you care about, right? So in the tree evaluation case, it would be a number 1 to k. In this case, just think of them as natural numbers. And their proof uses 3 registers, which means their memory is going to be something like 3 log n bits, which is the log space that you want. So what's the point of this abstraction? It's going to be the types of operations that we apply to it and the kinds of goals we want to accomplish. So to the point of using space for two things at once, you can think of a register as initially holding some stored values. So here are the values that we want to remember for later. And then there are other values for which we want to do some current computation on. And the important thing is that this plus sign is really a plus. If you were to look into this register R2, all you would see is the value 94. So which part is storage that you want later and which part is computation that you want now? It's completely indistinguishable if you actually look at the memory. Nevertheless, what they show is that you can add the computational values that you want to your storage, and from it derive a new value, which is the computation that you actually care about on those values. And in the same way, you're going to be adding it to some other part of your memory. And the point of this arithmetic flavor is that you can then subtract off the values that you cared about before and get back exactly to the storage that you wanted. And so in this cyclic fashion, they find a way to use memory that's already being filled with stored values to do computation as well. Now, this is very bizarre, but we're going to see it in action. Here's the lemma, the style of lemma that they prove. They show that if you're given one of these sharp NC1 circuits, C, then for every gate in the circuit, there is some program whose types of instructions I'm not going to formally define. But the program's, what the program does is it adds the value computed at that gate to some register in the memory, say R0, while leaving the other two completely untouched. And most important, this program works no matter what was already being stored in R0, R1, and R2. So that's the flavor of their results. And just to see what that looks like, if you have some values tau 0, tau 1, tau 2 in your register memory, then the program PG, the effect is just going to be to add this value VG. Again, in a way that you can't really distinguish between what's tau 0 and what's VG. It's just going to be one number, but that's going to be the operation of the program. And if we can accomplish that, then obviously we can actually compute the whole thing, because at the top, we're just going to run this on our initially empty memory and get the output value plus 0, aka just see the output value. So the reason I'm doing it for every gate, of course, is that it's going to be some kind of inductive argument. If I can compute the values of two children, then I can compute the value of their parent using those programs. So let's see how that works. The base case is trivial. So if I want to do this for a leaf, then I just take whatever value is there. It's sitting in my input. So I just look at it and I add it to whatever register I want.
The registers are not cleared in the beginning, or you don't care?
Well, I'm saying at any, the base case is really at any point in the operation. Yeah, I'm saying the base case for the actual lemma as I stated it. This is really the only application that you care about, but of course, every one is going to use other ones. So this is our base case in the sense of the circuit itself. The plus gates aren't that much harder. So I'm going to assume now, of course, that I have a program to compute the left child and a program to compute the right child. And now all I want to do is compute their sum, and compute in this sense of adding it to memory. Well, okay, I just run the program to add my left child, and then I run the other program to add the right child. And okay, now I've added the sum. So not much to be done here. Obviously, the tricky part is times. So the question is, how can I use the fact that I can add the left and right children to memory to add their product when I can't even see what's the difference between the value I care about and the value that's being stored, that's going along for the ride? So for this, I'm going to need two small tweaks. The first is I can pick any register that I want to add my memory to. Of course, it didn't matter for any of these things, whether it was 0, 1, or 2. So I'll use the subscript to denote which value I'm adding and the parenthetical to denote which register I'm picking. And I'm also going to need the inverse programs. I alluded to this earlier, but I need to be able to subtract values as well as add them. Again, the two things that I gave you before, instead of adding a leaf, you can subtract a leaf. That one's atomic. And then for a plus gate, if I assume I have the inverse programs below, I just apply the two inverses instead of the two forwards. And that subtracts the sum. So inductively, I can assume I have this so far. And now I'm going to use these things to compute the times gate. I'm going to motivate this however I can, but if you don't follow along, don't worry too much about it. So I need the value v1 times v2. I got to get it somehow. So why don't I just do it the easiest way possible? I'm going to add v1 to one of my registers. I'm going to add v2 to one of my registers, and then I'm just going to multiply them together. This gives me my value of this register R0 as being whatever was there before, plus the product of these two register values. And if you expand that out, it has this tau 0, which you do want to stick around. At the end, you want this to still be there. You have the v1, v2, which you also want. That's like the only value you care about. And then you have a bunch of junk terms in the middle. So now I have to get rid of these junk terms. Well, let's say I focus on getting rid of the v1 tau 2 term first. This is not so bad. I can just take my v2 out of this r2, multiply them together, and this time I subtract it. Right? So now I have no v2 here. If you multiply these together, you get a tau 1, tau 2, and you get a v1 tau 2. Subtract it off. So this actually not only cancels this term, but it cancels this term. So that's good news. Now let's do the same thing for tau 1, v2. So I'm going to run the backwards instruction for R1, so get rid of the V1 in here. Run the forward instruction for V2, so put the V2 back in here, and then multiply them again and subtract off. So this gets rid of the other junk term. And I could have done these in either order, of course. So this gets rid of the extra junk term, but I actually have a minus tau 1, tau 2 that's now along for the ride because I have two minuses and one plus. And this one's easy to deal with. You just finally get rid of the last thing, which is reset the R2 register, multiply them together. You just have tau 1, tau 2, you add it, and this cancels out the last junk term. So this was sort of the greediest approach possible. Get the V1, V2 that I want, and then get rid of the junk terms one at a time. And a nice byproduct of this is that R1 and R2 are back exactly where they started. So I've accomplished what I set out to do. R0 is tau 0 plus V1, V2. And that's product. So that takes care of our last case, and we're almost done. This means that our memory, we have to analyze our memory. So we used 3 of these registers, each of which we assumed only had, say, log n bits. So that part is log space, and that's efficient. We set aside some logarithmic memory for anything we need to do, reductions or doing field operations like actually computing plus and times, whatever. And then you actually have to keep track of your runtime, right? I need to know which instruction I'm running at every point in time. And so I need to keep track of where I am in this circuit. You can think of this as also being the stack of recursive calls. Well, if you go back to what I outlined, the program for a times gate made 6 calls to stuff below it and made 4 other instructions, 4 basic instructions of just combining the memory. And so if you just solve the easy recursion, the runtime is going to be 6 to the depth of the circuit, which we assumed was logarithmic, times some polynomial for the basic instructions. And so the whole thing is a polytime operation and can be kept track of in logarithmic space.
Probably one should stress that both this result and Barrington's result are far from being read once. They keep accessing the same inputs many times.
Yes, so one of the two restrictions I told you about for tree evaluation, for which we know good lower bounds, is this read once condition. But considering you're making, just in this part alone, you're making 6 different calls to the level below you, means you're gonna have to recompute the same value like 6 times, or even, in fact, it turns out being 6 to whatever height you're at. So you're reading the leaves, for example, tons and tons of times. And this gets around the read once restriction. Thank you, Avi. I might actually discuss the thrifty restriction when we get to it as well, to see how our the algorithms we're going to see dodges it. Regardless, this is the Benner and Cleve result, and so this is how you can get around the conjectured log squared lower bound in the case of these nice simple functions, plus and times.
For those who like arithmetic complexity, what they actually do is compute, think of it as evaluating a polynomial. You know, inputs are variables, these are plus and times, you evaluate some polynomial. Polynomial that can be computed in log depth can actually be computed with constant number of registers.
Yeah, this sharp NC1 class is more structured than, say, VP, the more general arithmetic circuit class, but it's still a very interesting subclass of it. Yes, good. So I want to now pose a question. Let's say I give you a function f that you want to compute, and I give you a string that I want you to remember while you're doing this computation. So I just give you a Turing machine, which has an input tape that's filled in with what I care about, but also the work tape has some string z in it. How much space does it take to actually do these two tasks at the same time? How much space does it take to compute this function f while you're remembering this string z? You can obviously do it by just setting aside the space that you used for z and doing a fresh computation on the rest of your work tape. The space complexity will just be the sum of the two. And the question is that tight? Can you do it any better? The conjecture of Cook et al., if it holds true, it essentially hinges on the answer being yes for pretty much every f. So in other words, you can always find functions to plug in on the interior nodes for which this is basically true. Remember, you were remembering the left node while computing the right. Remembering the left node while computing the right. This was the argument that we said would require log squared space. This hinges on the fact that you can't use the memory that's already being in use for saving the old values for computing new values. So that hinges on the answer to this question being yes. But what Benner and Cleve showed is that if the functions are sufficiently easy, plus and times, then it doesn't take any extra space. You can do it in like the max of these two, roughly speaking. So I'm going to take a brief detour into a model called catalytic computing, which was introduced by Berman, Cleve, Koski, Loff, and Spielman, where they said, let's just model that question directly on its own terms. They introduced a variant of the usual space-bounded Turing machine model. So here you have the usual read-only input tape, you have your write-only output tape, and you have your work tape, let's say logarithmically bounded. In addition, I'm going to give you a new work tape, which I call the catalytic tape. Think of it as exponentially bigger than this work tape. So you have polynomial amount of working memory available to you. And the catch, as to the question that I just asked, is that it's completely filled in already. It's filled in with some string that's outside of your control. And at the end of the computation, it had better be in exactly that same configuration. So if you can use it and reset it, then it's all yours. But the natural question is, I mean, does this do anything? So I said, think of the tape as logarithmically bounded and the catalytic tape is polynomially bounded. This is called catalytic log space because corresponding to the work tape, you can instantiate it in other cases, but this is the one we care about for today. And the big question is, what can catalytic log space do that typical log space can't? Because a priori, it's not obvious that this thing helps you at all. You could try and compress it, but of course it might be incompressible. So you could move it to the work tape, but then you're just going net neutral. It doesn't seem like there's any reason why the catalytic tape should help you, but I wouldn't be taking this diatribe if it didn't.
Also in chemistry, it's not obvious that catalysts should help, but they do.
Yeah, there's actually, I think, 4 different definitions of catalytic computing from different areas of computer science. And they're all based on the same chemistry metaphor. Give it a resource that has to still be there when you get to the end of the computation, but that somehow helps you. They're completely unrelated and incomparable. Most of them are network things, I think.
So you said this was modeling the issue of whether space of FZ is space of F plus space of Z.
Yeah.
How?
So this is modeling a version of this question. So this question models it. If CL can't do anything that log space can't, in other words, if CL equals L, then this is saying for any of these problems that are computable, for any problem that is outside of log space, this additional space doesn't help you to do anything.
Here's the context of the content of the catalytic part.
Yeah. So think of
I
this,
see it.
sorry, the orange thing was a bit tenuous, but yes, think of this as being the string Z. And so if you can compute something in less space than space to compute it F plus Z separately, then you can get a problem outside of log space, hypothetically, just inside this log space work tape. So this is a version of the problem. And so speaking of which, I'm gonna throw one more class at you. TC1 is again a Boolean circuit class of logarithmic depth, but instead of fan in 2 ands or ors, I'm going to give you majority gates with as many inputs as you'd like. So this is a very powerful class. In fact, we know that it contains non-deterministic log space, and it has functions that we do not think are in NL, let alone L. So a version of the determinant is in here, for example. And, well, I'm introducing it because this result of Berman et al. Showed that catalytic log space can actually capture this class TC1. In other words, just by giving you this possibly incompressible auxiliary work tape that you have to reset, you can capture all of non-determinism and more. So this is pretty, I think this is quite surprising. And the nice thing for us is that the style of the result is very much what we saw in Benner and Cleve. They show that for every gate in the circuit, there exists a program which can add the value of that gate to some spot in memory and leave the rest of it untouched, where now the gate set is these majority gates. And the reason that this helps you is because you can think of now your register space as being this catalytic tape, which is completely filled in, because all of the programs that we design are agnostic as to what's already in the registers. So at the top level, you can allocate just a little bit of your working memory to be that register to get your answer written in pure space. And all the rest of the computation is going to happen inside this polynomial length catalytic tape. So that's the power of this kind of lemma. And I want to take one more step into this and say that the first thing you have to do is convert majority into an equivalent arithmetic form. So they show that, all right, these are the inputs, x1 to xm. If you take their sum, you get just the number of bits that are 1. And let's say that number is actually k. So if you subtract off k, you get a 0 in here. And if it's not k, then you get something else. Then if you raise it to p minus 1 mod p, we know by Fermat's little theorem, this thing just becomes 0 if and only if the number of ones is exactly k. And we're going to flip, and 1 otherwise. Flip that, so it's an indicator of whether or not there's exactly k ones, and then check for every possible value from n over 2 up to n. And this is a majority gate.
Or any symmetric function.
Or, yeah, you can do any symmetric function by just adding up over the ones of the function.
And p is some number bigger than n or.
Yeah, pick p to be the nth prime or something like that, or the s prime, where s is the size of the circuit. Just something big enough. You can always find these things. I only go on this detour to say that what they actually do is design a program that can compute unbounded sum and a program that can compute powering. So the arithmetic, as we saw before with this plus and times, it's important to have this nice arithmetic form where we know how to add and subtract and multiply and all this. And it's also important to get the right efficiency. Here, polynomial number of registers is fine. We have this huge catalytic tape, which can be poly length as big as we want. So poly n registers, log bits per, all of this is fine. The important thing is that both of these make, again, just a constant number of recursive calls. So with the depth of the circuit being logarithmic, the runtime ends up, again, being polynomially bounded. And so you can keep track of how long you've been running on the log space work tape, the free memory, and do your operations there too. And everything that you would want to do fits into the log space work tape, besides the actual values, which are all being dealt with just on the catalytic side. So that's the way that they go about this. So that's as deep as we're going to go into this one. I just wanted to stress again the arithmetic part and the how the recursion plays into your space complexity. Yeah.
This is probably a silly question, but where, like, why are you using the catalytic tape? Like why can't you just do this in actual log space?
Because even just to store, say, m values, think of m as like poly n, just to store these values takes like a polynomial space. You're not. So I'm lying a little bit here. You don't have a recursive call for each gate. You have a recursive call for each layer, because if you had to do each gate separately, you'd get like a linear blow up at each level, and it would take quasi-polynomial time. So you actually have to compute a whole layer at a time using the whole layer below it.
Oh, so because gates have fan up to n.
Yeah, exactly. The gates have unbounded fan-in, so if you want to deal with these things, you're going to need to store all the values, and that's going to be polynomial.
But if the gates have fan in like less than n, like log n or something, then.
So again, there's like since I'm storing numbers mod p, and that's like n, you're gonna need a logarithmic number of bits for some of these registers. So if it's like log fan-in, it might be log squared. There are actually they're a bit non-standard, but there are circuit classes around right inside TC1 where the fan-in is bounded by a logarithmic amount and whatnot, and we do know some results there. But in general, here we're just willing to be lossy.
The different, I mean, there are many circuit classes that come in two varieties, bounded fan-in and unbounded fan-in. I mean, you can have intermediate like log, but anyway, bounded or unbounded. And as a trivial inclusion of, you can always pay a log to move from unbounded to bounded, if polynomial size. And this is the whole game, playing on this logarithmic gap between NC1 and NC2.
Yeah.
TC0 is, or TC1 is between NC1 and NC2, and you wonder where it is, but it's about, yeah.
Yeah, so
somehow log space is somewhere in the middle, and we are trying to understand.
yeah, an example of what Avi's talking about, when I put TC1 on the class here, I actually put it inside NC2. And that's because you can just create a log depth formula to compute a majority gate and replace every majority gate with it. Then if you apply Barrington's or Benner and Cleve and whatever, you're going to end up with pure space like log squared n, because the height of the thing is log squared, or the depth of it is log squared. So you can just do, or actually you can do more naive calculations and get it into log squared n space. But yeah, that's neither here nor there. So here's the question again. What is the space to compute f while remembering z? And the point is just that we're now showing harder and harder functions for which this isn't true, or more situations in which this doesn't hold. So before we move on back to tree evaluation finally, are there any other questions? All right. So this is how I won $100. We showed in 2021.
Which cook it is.
This is Cook Jr. He and I were paid out by Cook Sr., his dad.
Only in the family.
Yeah, so I, of course, was Steve's master's student and James is his son. So we've kind of accrued way more than $100 from him over the years in favors and services rendered, but he felt fit to give us the money anyway, so oh well. Right. So this was our result from 2020 and then kind of squared away in 2021, where we showed that tree evaluation can actually be solved in less than log squared space. We shaved off a very small log h factor, but this was enough to get a log n savings. Yes, so here's tree evaluation again, because you haven't seen it in a while. And like I said before, the first thing that you need to do if you're going to deal with this in this framework of register programs is turn everything into arithmetic. So before you saw arbitrary functions and values 1 to k, now you see log k tuples of f2 elements and polynomials over f2. These are the same thing. You know, by interpolation, all these functions could be thought of as polynomials and there's no issue. So now the goal is, instead of computing unbounded fan-in plus, fan-in 2 times, powering to this p minus 1, we just have to compute arbitrary polynomials this way.
Maybe the comment about this, it appears again and again somehow that you need to compute Boolean things, and converting them to polynomials help. Two examples one can think of, and there are many more. One is Rasbour's lower bound for the class AC0P, AC0 computations, fast power unbounded computation, where you can also do mod P. He converts it into polynomials and then prove weakness for this kind of model. And another is the results of Ryan Williams, where he how do you call this complexity, this fine-grained complexity, where he shows surprising upper bounds where you need to compute some Boolean thing, you move it to the polynomial setting, and then you can parallelize things, let's say using interpolation, fast Fourier transform. You can, somehow parallelize things that you don't obviously see how to parallelize in the Boolean setting. So it's a very powerful tool, and that's another example.
Yeah, it should even be mentioned that this whole idea of getting lower bounds via composition is maybe, well, you can maybe comment on this, but is based a lot in our intuition about monotone circuit lower bounds, for example.
Yeah, but I would conjecture the KLW conjecture also for arithmetic.
Really?
Yeah, I do. Yeah.
Oh, all right.
Yeah, it's on the paper, but I've many times mentioned.
Okay.
So that's a separate issue. But
I see. Well,
not everything can be done faster in arithmetic.
well, we'll see. But this is one of the big techniques that we know how to do against monotone, right? That we know how to do non-monotonically, which is this arithmetic flavor where you get cancellations or reversibility or whatnot. So in some sense, it's nice that this is the technique that worked out.
It is, yeah. No, it is very powerful. I can let me say it then, just as you, the arithmetic version of KLW. You have two polynomials, and you want to compose them, namely the input f and g. You want if the inputs to f are, I don't know, xi, then you feed into each one the value of g on fresh set of variables. So the most natural way to build a formula for composition of f and g is like a tree. You evaluate f, and that will leave you evaluate g. So the formula size should be, or it's at most the product of the formula sizes for f and for g. This is true for Boolean, for arithmetic, for whatever set of gates you want. And the KLW conjecture of the philosophy is that you cannot say much in general for arbitrary f and g or for randomness.
Yeah, I skipped over the compositional logic for formulas earlier when I said this KRW conjecture says that tree evaluation requires formulas of depth d times h, and what Avi just said is sort of the reason. So you have, again, think of f as one of your tree evaluation nodes, and the g's are from the ones below it. Well, if you plug these g's into f and you ask what can you do for formulas, it seems like the best thing you do is just replace every leaf of f, which used to be a value, with a formula for g, optimal formula for g. This would be depth of f plus depth of g. If you compose this over h layers, your total depth is like d times h, where d is the fan-in, because you just plug in a maximally inferred function, which requires depth d circuits for d inputs. And that's where the d times h comes from. But of course, the conjecture is that this is really the best thing that you can do. And well, we are going to talk a little bit about the KRW conjecture at the end of this talk. So here's the style of lemma we want to prove. For every gate in a circuit, there exists a program which adds the value of that gate to one of the spots and leaves everything else untouched. And now we should think of the gate sets as being polynomials or even tuples of polynomials, arbitrary. So that's the style of result that we want to prove in the vein of what we've already done.
You still want a constant number of this.
And if you want to get this optimally, you will need a constant number of recursive calls. So each PG should only call the layers below it a constant number of times. That is not what we're going to accomplish, but we will get close. So we do get a good amount. Wait a second. Oh, yes. So this is I'm still talking about the earlier result. This is from 2021. So what we proved is that you can do exactly the lemma that I specified with a very efficiently with respect to register space. So you need exactly the amount that we needed for this earlier Benner and Cleve thing, where instead of now holding 3 values, we're holding 3 log k tuples of bits. And the 3 is according to, we need to store the left, we need to store the right, and we need to store the value we're computing. And we use them in cyclic fashion. So 3 log k registers, each of which holds a bit, log space. The number of recursive calls, on the other hand, is horrendous. So these are polynomials with log k bits, log k inputs, and the number of recursive calls we need is something like the number of monomials. So it's exponentially bigger than the size of the input. And if you just work out the recursion for this, you have k squared at each level to the layer below, so it gets raised to the h, and then you take the log of that because that's the actual number of bits to keep track of the runtime, and you get h log k, exactly log squared n space as Steve Cook conjectured. So that's not a proof. The important thing about doing this trick was that the number of recursive calls, I said it was like the number of monomials. What it really is it's exponential in the degree of these polynomials. So it's a slightly sharper trade-off, and that is actually enough because what we do in the paper is we do some encoding tricks to store values in k into a larger space where the polynomials representing them then have lower degree. So one example would be the one-hot encoding, right? You have k bits and only one of them is 1, whichever the value is. If you think of combining 2 of these things and getting a value out, that's a degree 2 polynomial. You just look at 2 spots at any given time. But of course, the space usage there is like k here, so it's really, really bad. It's linear space. The point is we make trade-offs, and this is how we get our log savings. And the reason I'm going into this diatribe is to say that if you can get fewer recursive calls than 2 to the degree of the polynomial, this immediately translates into faster tree evaluation algorithms by way of what happens when you unravel the recursion. And this translates directly into smaller space tree evaluation. So our primary goal was to take the lemma that we had proven about computing arbitrary polynomials in this way and reduce the number of times you have to access the input. That was our goal, and that's what we did. So we recently showed that you can solve tree evaluation in space log n times log n. So before we had shaved off a log factor from this log squared conjectured lower bound, now we're just that same factor away from a log space algorithm. At this point, you could still believe that it's not in log space, but I think it requires a lot more faith than it did before. I certainly don't believe it. The way it happens, as I was alluding to, is that we make only, instead of exponential in the degree number of recursive calls, we do it in linear. So we can show how to compute an arbitrary polynomial by only calling the inputs linear in the degree number of times. Where again, calling the inputs means adding it into memory that's already full. That gets us our h log k, which is the log n log n. We do make a small sacrifice though. Before we had 3 log k registers, each of which was just Boolean. Now we actually have to embed everything in a slightly bigger field. So the field size blows up to itself be linear in the degree. But it turns out this doesn't matter for the space. So then you have to, for each register, you have to store the one of these values. The degree is like log k because there's only log k inputs from the left and log k from the right. And so to hold a value from 1 up to log k, which is the field, you just need log k bits, and this gives you your algorithm. No problem. So I want to show the whole proof.
Yeah.
Can I do it?
Yeah.
All right, great.
So you're evaluating any polynomial with the
Any polynomial,
degree number of recursive cores as opposed to.
yeah, so for you,
Polynomial number of.
you can forget about tree evaluation now. Just think you have a polynomial sitting in front of you and you have a magic button. When you press it, it adds all of your inputs to some full memory, your catalytic tape, think of it as. It adds it, mod whatever field everything is in. And if you press the button again, it takes it back out. So using these button presses, you have to now compute the value of the polynomial and add it to some other spot in memory. That's our challenge. So we're gonna have to pick some field K. Again, we're not gonna be able to do things over F2. We're gonna pick some field K, and here's what we need out of it. There's gonna be a number M, which again, I will specify in a bit, for which we need roots of unity of order M and inverses of M. So the number M has to exist in K, as does its inverse, and there has to be actually a primitive root of unity of order M. And a primitive root of unity is one satisfying these two properties. You can define it in an even baser way, but we'll just use these two properties. So the first is that if you raise it to the mth power, you get 1. And the second is that if you sum up all the powers from 1 to m, you get 0. So that's
And M would be like N or power of N.
say again.
M would be something like N or power of N.
M is going to be, yeah, just give it away. M can be any number that's bigger than, strictly bigger than the degree of the polynomial. So degree plus 1 is fine. And we'll see why in short order. So I'm going to adjust this condition a little bit. I'm going to say even if you take the sums from j from 1 to m of omega to the b to the j, then this thing equals 0, as long as b isn't a multiple of that. It doesn't have to be coprime. It just doesn't have to be a multiple.
You said b to the j, but it says j to the b.
B to the j, omega to the j to the b, or omega to the b to the j. It's omega to the j times b.
Why don't you take a
Oh, so it's j
primitive?
times b.
Yeah, times b times b.
Yeah, why don't you take a primitive one and then you won't have to.
Oh, this is, this is a fact that is known about primitive roots of unity. Like you could, it's a couple line proof from this fact to this fact. I'm just saying that we're going to use this stronger version of it. Yeah, in fact, you don't even need to define it this way. You can just define it as every other power between 1 and m minus 1 is non-zero. And that's enough to get this thing.
Sorry, just to go back to like from the circuit eval problem,
Mhm,
tree evaluation problem. What is the degree in that in like that?
Good.
Depends on the encoding they use.
Well, yeah, so let's pick the most naive encoding. These are, you start with bits, log k bits on the left and log k bits on the right, right? You're just specifying a number in binary on the left and in binary on the right. So this thing, since it's over, these are f2, x squared equals x. So the degree will never be bigger than like 2 log k. Yeah, so that's where the, so, okay, I went a little bit too far back. Here, yeah, k squared is because it's 2 to the 2 log k. And likewise here, this degree is 2 log k, so you get this inside. Is that fine?
Yeah.
Cool. I'm going to strengthen this thing one more time. And this one's really trivial. And it's that if I pick a b, now it can be a multiple of m. Specifically, it can be 0. Then if it is 0, then you get this sum is just m, and otherwise it's 0. So this is an obvious extension of this. In this range, there's only one multiple of m, and each of these becomes 1, and you sum m things that are 1 and you get m. So nothing interesting here. What's interesting is this key equation. The sum of j equals 1 to m, the product of I from 1 to d, omega m to the j, tau I plus vi. What is this thing? Tau I is going to be some value. Think of this as the catalytic memory. This is something that I don't want to actually do computation on. I want to keep around. And vi are the values that I actually care about. VIs are the values that I want to compute some polynomial on. So think of this as being what my register Ri actually looks like. I've prepared the register in such a way where it originally had tau I. Now I've multiplied this tau I by some power of the omega m, and then I've added to it vi. I've taken their product, and I've done this for every different power of j. So that's what you should think of in an operational sense. this value, if you just expand, if you just switch the product to the, if you expand the product as a sum of degree D terms or level B terms, you keep this outer sum. And now you're going to sum up over all monomial sizes, B from 0 to D, and you're going to sum up over all sets that have exactly this monomial size. And then what? You take the product of this stuff on that's in the set and this stuff that's not. This is just the binomial expansion of it, right? So this sum is the set S is picking which of these terms I'm having, and then which of these terms I'm having is everything outside of it. So this is the expanded form of it. I'm just going to move it up here. Well, you can tell that I can do a little bit of switching around. The J only appears here. So let's just move it out and flip these two sums. So summing over all the level B terms, 0 to D. And then this sum from J is 1 to M is only relevant to this term, which is the multiple out in front of all of these summons. So you get this as our coefficient, and on the inside, you just sum up over all of the monomials there, where now all you have is the taus, no coefficients inside S, and all of the V's outside of S. Again, just moving it up. And from this form, you can see this is where the equation comes in. So if you take this sum, you get the value M exactly when this B is 0. And otherwise, you're going to get 0. Subject to a fact that I forgot to write up here, which is as long as B, the value B here, never gets to the next value, a multiple of M. In other words, as long as D, the top end of the term, is strictly less than M. And that's why I said you can pick M to be one more than the degree. Or you can pick it to be anything greater than the degree. Because when we apply this fact, you cancel out every single sum end except for the term, which is, this is a value M, B is equal to 0, which means this set is 0, which means you have no tau i's, which means you have just the product of the VI's. And thus, the equation that I wrote at the start of this is just M times the product of the VI's. All right, well, that's the case where your polynomial is just the product of all the inputs. But if you want to extend this to a polynomial, it turns out you just replace this product with the polynomial itself. This additively parallelizes over every monomial of the polynomial. So as long as the polynomial itself has degree D or anything less than M, then considering each monomial in term, each of them is subject to this key equation. And sorry, I moved this M inverse here because you get a multiplicative M over here. So that's where the M inverse comes in. So if you just apply this equation, then you get exactly the polynomial evaluation that you care about. So this is the magic, and just you have to patch it into tree evaluation, but that's not too hard. So we're going to pick our field K of which we're operating over. Just pick it to be something of characteristic 2 to make all the math easy. We're going to choose M to be 1 less than the size of the field, because then the inverse of M is just -1. And also because you can pick any generator of the multiplicative group, because the multiplicative group has size M, right? It's every number except for 0 is the multiplicative group. So this is the easiest way to pick the numbers. As long as you can find this thing in log space or anything satisfying the conditions, you're fine. This is just the way we chose it. Your registers are now going to be values stored over this field K. And to implement what we actually want, if I loop over all values J and I prepare the register in the state that I wanted, I'm going to be multiplying whatever was in Ri before, which was this tau I value. I'll multiply it by the appropriate value of omega m to the J, and then I'm going to press my special button and add the input. And that puts the register in exactly the state that I want it to be in. Likewise, if I had that state before, I just do the opposite, right? I press the inverse button to subtract out the values, and then I divide by omega m to the J, and this gets me back my original value.
If you want to add this over all J, right?
And yeah, this is for all J's. So I haven't told you where it goes. In between these two things, this is how you go forward, this is how you go backwards. And in between, you're going to choose your output register. This is where you actually want the polynomial to go. And you're going to add M inverse times the polynomial applied to the values in those registers. And since you're doing this for all j, what's in R out is tau out, whatever was there before, plus the sum of these things. By our equation, that's exactly the polynomial applied to the inputs. And the number of recursive calls, of course, is 1 here, times m, 2m, and I said pick m to be roughly the degree, just one more than the degree or something. And so the number of recursive calls is linear in the degree. And moving back to tree evaluation numbers. So now you're starting with log k and log k. You pick your field size to be roughly 2 log k, and m is the same. And so your space is 3 log k registers, each of which holds a value in this bigger k. I don't know why I picked k twice. Sorry. And the time, well, you make that many recursive calls, like the field size, raise it to the h. And so the total space is this plus the log of this. And that's h plus log k times log.
It's not polynomial time.
It's not polynomial time, no.
It's not-
This time, part of the log n space usage is just to keep track of the runtime, which itself is, n to the log n.
Okay.
Yeah, because it's log n to the
Yeah,
log n,
yeah,
so it's n to the
okay,
log n.
No, the size of k is polynomial. Oh, sorry, the size of k is.
Logarithmic, it's log, so everything gets scaled down because you only have log k bits coming in.
Right.
Yeah, if you pick your representation worse, your numbers will change. And we had to pick representations in our first paper. In this one, everything just works with binary, which is nice. I should also mention that this works for the higher Fanon version. You have to replace all the 2's that you saw before with d's. And when you substitute d into the equation and then look at the actual size of tree evaluation, you get exactly log n again. So there's no issue with taking the more general version. And that's relevant because of the KRW conjecture. So at the beginning, we saw that there was this long-standing conjecture that tree evaluation with this unbounded Fanon parameter is not an NC1. And if you put our previous fact together, this shows that now, if you could prove the KRW conjecture, you would no longer just separate NC1 from P, you would separate NC1 from L. So you would show a separation between formulas and branching programs. So this is a very, very sharp separation. In the complexity class list that I gave at the very beginning, there's a whole lot that's resting between L and P. There is basically, sharp NC1 is the only class that we care about sitting between NC1 and L. Like, they're very closely related, and this would be a very nice separation. As I also said, this is an interesting one. So we picked tree evaluation at the very beginning of this talk, as opposed to circuit value problem or some p-complete problem, because this compositional logic had a nice flavor, and we thought we could reason about it. And so if you want to prove the KRW conjecture, and you have more intuition about composition than anything else, then that should still be what you go for. But just as it's formally easier to prove circuit value problem isn't an L, it is now formally easier to show that undirected ST connectivity, or even directed ST connectivity, is not an NC1 than to show tree evaluation is. We have no idea what the hardness of tree evaluation is. We don't know which classes it's hard or easy for so far, but at the start of this, before all of this work started, we thought it was, some pretty hard problem. It would be easier to work with that than, say, ST connectivity. Now we know that's not the case, because if you take a padded version of tree evaluation, it reduces to ST connectivity.
It's easier because of the results on catalytic space that analyze in. Why is it easier for?
Well, it's formally easier, right?
Yeah, why is it formally easier?
Because
There is a reduction. Tree evaluation can compute ST connectivity.
tree evaluation cannot compute ST connectivity as far as we know. No, actually, we have no idea what tree evaluation is hard for.
Formally easier. I'm missing something.
The other way around.
Oh, the other way around.
Yeah, the other way around. Yeah, no, before we didn't know which was formally easier to prove, but we had more intuition about tree evaluation.
True.
Now at least we know.
And is there a reduction from tree evaluation to ST connectivity?
No idea. Tree evaluation is this weird problem which characterizes, you can think of it as like just a generalized circuit model, right? Take NC1 If you give it arithmetic, it's sharp NC1. If you let it do arbitrary things, it's like word NC1. That's tree evaluation. What is that class? We've got no clue. We don't know if it's, if L reduces to it. We don't quite know yet if it reduces to L, although again, it seems quite likely. Maybe there's a separate class that is comparable to, but again, there's not much in that range. So it's really unclear what tree evaluation characterizes, and that would be a very nice problem. Showing it's complete for L would give a cool flavor of log space in this sort of parallel circuit form. So I'd love to know what it's complete for. And of course, we still need to get it in L. So if you have any ideas, please let me know. Catalytic is really cool. And these techniques are, I think, counterintuitive, but quite beautiful and interesting. It'd be nice to find other things to do with it. Right now, we're just focusing on space upper bounds, either in the catalytic model or in the classic model. But these techniques have a little bit of reach. You see these same sorts of XOR bit tricks and stuff like the network coding conjecture and whatnot. And it'd be good to bring the tools that we have to bear on other questions outside of just classic space-bounded complexity. And speaking of which, I wrote a survey on this kind of stuff a few months ago for a bulletin of EATCS, and it's also on ECCC now, which goes over these techniques a little bit slower and also talks about potential areas where it might be useful or which might be useful for catalytic as well. So please take a look. I have a number of other results in the paper on branching programs, so I have extra slides, but for now, I'm going to just say thanks.
Great, so questions?
So the main identity that you proved, it's basically like a depth 3 circuit that's 0. Is there anything that it says about identity testing depth 3?
Oh, that's a good question. I'm not sure. That key equation, I mean, we found it one way, but it pops up. First of all, it's basically the Fourier transform if you look at it in the right way. It's just these like omega to the JBs or like the right values in the matrix. So if it shows up there, it's also kind of like what you do in error correction, right? Like testing a bunch of points of a polynomial to get to the one that you actually care about. I haven't thought about identity testing specifically. I guess that would be a deterministic sort of test because you know which points you want to check, but then you would have to know that the point in the center that you care about, this evaluation of the VIs, is something interesting. So I don't know, you sort of have to design these points with that in mind already. And I don't know why you wouldn't just test the polynomial on those points. But I can see equations like this being useful if you know where to get the right cancellations. I'm not sure.
It's a bit of a silly question. How do you compute the primitive root? You just try like all the values in your field until you find one? Or?
Any element is a primitive root in, if you were multiplicative to
Any element?
to the R.
Any generator. Yeah, we have a little section on the paper on it. You don't have to try anything. I think there's some standard ones that are known to be generators in the multiplicative group for.
Not for every exponent, for some exponents. For some exponents, not for every.
Okay.
Like,
Well, you can always you can always increase this exponent a little bit. As long as you can find it in some range, as long as you're asymptotically at this is plus order 1 or something, you're gonna get the same asymptotics. So it shouldn't be a big issue. And also I forgot to say field arithmetic in this can just be done in small space. No issue there. Yeah, can you search? I guess you could just search in log space at the beginning and you wouldn't have any issues.
And that's fast enough for what you need.
I mean, you can test every element's order separately because you can parallelize, right?
I see.
Yeah, and you only need to find this thing once because you can just use the same M for and omega M for the entire thing. So just put it aside, at the beginning.
That's fast enough, I guess.
Yeah. There's well, at least it's space efficient enough, right? Because you just test every element and then just do the powering. Yeah, so it's no problem. Also, I didn't quite say how to, this came up in a question before. I didn't quite say how to actually implement this instruction in log space. It's not hard. These values are sitting right in front of you. And the polynomials coefficients are all written in your input tape. So you just kind of go in and evaluate term by term. This is just like a low degree extension of your original F2 function. So it's no big deal.
Oh,
Could some higher depth version of this key identity reduce the number of recursions that you need?
Reduce the number of recursions that you need. Reduce the number of, all right, so. So I said we want constant number of recursions, but since I gave you the one-hot encoding idea, I can tell you that actually there is a way to get the number of recursions to be order 1, regardless of the degree. And the only problem is that your memory is now itself like 2 to the degree. And the thing is just basically storing the entire polynomial in one term, like all the monomials at once. So we know you can get it down to a constant number of recursions, but for a dumb reason. This one, like implementing these kinds of equations more efficiently, it's hard to tell. How can you do a constant number of evaluations and converge on this point? Seems tricky. Maybe you could borrow some of the extra memory for it. But since we're right at the threshold where both of them are like log n, log n, it's not clear exactly which trick will help or which ones should be feasible. But at least I wanted to bring this up to say that if you think that there's some strict lower bound against the number of recursive calls to do this, that's not true. There might be a trade-off result, but now I don't know what it would be, considering we have poly and constant 2 to the degree, whichever way you choose it.
I have a couple of comments. Or maybe some of these is mentioned in your survey, I don't know. So I think in the whole talk you mentioned the reversible computation only once.
I know to cut away.
But this fits very well with the studies in the 70s, a paper of Bennett on what can be computed in a reversible manner by gates or by operations that are reversible. And it's still not well understood, and in particular, there are partial results of I give you a log-space machine, and you want it over a reversible computation, what space do you need if you want to? And you lose something, and there are very interesting results. But one particular, once quantum computing came on the scene, reversible computation automatically came on the scene because everything happening in quantum is reversible by definition. And so I'm wondering whether these techniques are useful for any quantum algorithms to say space. Space is a serious issue in quantum computing. Although the Regel just had a implementation of Peter Shor's algorithm for factoring, which the normal one needs n square space if n is a number of digits of the number we want to factor, which was a big issue. And he has a new algorithm which reduces it to n to the 1.5. So I just wonder if these are relevant for
sure. So here's BCKLS, who introduced catalytic computing. Michal, do you work on quantum?
No.
Okay, so everyone except for the K is primarily a quantum person.
Yeah, no, maybe that's the word.
As are Benner and Cleve, but
Yeah.
for example, the comment that I made earlier about this being the Fourier transform, one obvious thing you could try and do is instead of these taus being part of your memory, embed them in the coefficients of your qubits, and then apply stuff like the Fourier transform in that sense, which can be done in the QFT is very, very efficient. So you could ask for questions like, is tree evaluation in quantum log space or even quantum NC1?
Yeah.
Can these tricks, I think your question was more, can we use these kinds of ideas to do something for quantum? You'd have to look, I suppose you'd have to look into the coefficients to what it means, what it would be like to use these taus as the coefficients. Because if you just use computational basis states, like, yes, everything parallelizes across, but there's nothing, we haven't seen anything that's really interesting there yet. The question is.
The game is not for log space, it's for linear space.
Yeah, exactly.
Space or something.
Right,
Yeah.
So.
They pay dearly for each quantum bit, right, physically.
Yeah, no, it'd be really nice to, I think probably a lot of this did come on the scene because of the study of reversible computation in quantum. As you said, there was this reversible space equals space idea that came out in the early 2000s. And there's even a catalytic space equals reversible catalytic space. So you can just think of these operations in the same way. So there's a lot of, deep reversibility connections here. There hasn't been a formal connection drawn to quantum, because there's a few barriers you have to get over. So for example, let's say you just want to prove quantum Benjamin cleave, right? Like QL contains QNC1 or something. Well, let's start with the kind of easier scaled down version.
Let's say you want to prove
Six
L contains,
QNC1 or something like that. Even showing BPL contains BPNC1 is not known because of the read once versus read multiple randomness issue, and things you would try sort of actually fail in surprising ways. Then when you move to quantum, it's even worse because you have to deal with these long range correlations. And so you need to do something like catalytic space where you're storing everything at once. Otherwise you're going to lose, we don't have local computation anymore. NC1 is local. So there's a lot of these kinds of pitfalls to just trying to get even the basic, or reproduce the basic results that we know in quantum. But I think that there's hope to work these out. And if we can get those kinds of results reproven, define quantum catalytic and show that it can do quantum TC1 or whatever, then we have I think we have a good shot at showing something far beyond what we have in the classical world. Because these should be powerful models, especially when you can consider entanglements, when everything's reversible and you have stronger reversible instructions, etc. But I don't know what they'll be yet.
oh, it's interesting. My last comment is actually, I don't know why I never thought about it long before for Barrington or Benoit Cleave, but the way you mentioned it, how it combines storage and computation together. In my first class of my first year in undergraduate, I guess programming, they gave us an exercise. You have two registers, each contains a bit, X and Y, and you want to flip this. You want to put, you want to flip them. And you are not allowed to use any more memory. You can just use the storage. I remember thinking about it for 2 days. It's easy and you all know it, have seen it. But if you didn't do it, this is maybe the simplest example where
For sure. It works for two numbers as well.
No, of course.
And bits is like the easy bit tricks. I did a talk at a high school about a month and a half ago, and I gave them this exact exercise, and I phrased it in terms of bits. But I realized in retrospect, I should have just given it numbers, because then you don't have to say XOR.
Yeah.
And the idea of doing it in 3 instructions, good luck trying to do some if-then thing when you have every natural number or whatever at your command.
Numbers, it doesn't matter. Yeah.
That is a really
That's probably the best example I know with that.
And thank you for the plug. That example appears in the first paragraph of my survey, the bulletin of the EAT says. So if you like this trick, please up my engagement metrics.
All right, great, thanks, Ian.